Turning human-readable code like assembly code into machine code, the language a computer understands, is relatively easy. You could do it by hand if you really wanted to. But doing the reverse, turning machine code back into something readable, that's provably impossible. But you can easily find and download disassemblers online. So why is it impossible, and how do we do it anyway? I'm going to explain why, and if I fail to convince you, well, that might just help you ignore what's impossible and create a disassembler anyway. So if you think I'm full of poop at any time, keep watching. Maybe it's on purpose. And in case you think I'm just being pedantic and talking about how you can't get back comments and labels and stuff, that's not what I'm talking about. I don't care about that stuff. What I'm saying is, it's impossible to write a program where if you have some arbitrary assembly code, then simplify it so the memory layout is totally specified, all the hard-coded data is turned into simple binary data, labels are converted to actual memory addresses, there's no comments and no extra formatting, and turn that into machine code. The program can turn that machine code back exactly into the simplified assembly code. All the time, no exceptions. That's impossible. Maybe you noticed I made a pretty strict requirement here by saying the result has to be exactly the same as the simplified assembly code. Let's move on so we don't spoil anything though. To learn how disassemblers work, it'll help to know what an assembler is and what assembly code is for that matter. Really, we could be talking about any high-level language like C++, but assembly code is the simplest case, and maybe the most surprising, so I'll be sticking with that. I'll also be using Game Boy assembly and machine code for demonstration purposes, because it's a pretty straightforward architecture and it's the one I'm most familiar with. Okay, background. I'll give a quick summary of what machine code is, what assembly code is, and the basics of what an assembler does. Here are some time codes if you want to skip some stuff. Machine code. Machine code is the binary format used to encode the instructions that a computer directly runs. Assembly and high-level languages like C++ are meant to be readable by humans, and they need to be translated into machine code so that a computer can understand them. This is done by assemblers for assembly code and compilers for other languages. You only need to do that translation once, and it gives you a binary file that can be executed over and over without extra work. Languages like Python and JavaScript are interpreted languages that are run through a separate program called an interpreter every time you want to execute. There are a lot more details I'm glossing over. If you want a deeper dive, let me know in the comments. Anyway, I'm just going to be talking about assembly code and machine code. I'm ignoring the rest. Machine code is made up of a bunch of instructions that are represented as numbers, as binary data. A machine code instruction encodes two important things: what the instruction does, the operator, like add, subtract, load, jump, and what data the instruction is working with, the operands. The CPU has circuitry to decode that information so that it can do the right thing. Assembly code is the human-readable programming language that's closest to machine code. You could write machine code by hand. How do you write your machine code? And that's something you might want to do if you're playing with homebrew and retro computers. It can be fun, but not for very long. Also, it's super easy to turn a simple assembly instruction into a machine code instruction and back again. So we haven't hit anything impossible yet. Assembly code has some quality of life features that makes it easier to write than machine code. You can usually have your code in multiple files. You can write data in convenient formats like hexadecimal, decimal, or text strings. You can define labels to refer to memory addresses with meaningful names. And you can write code without knowing the exact memory layout ahead of time. It's the assembler's job to convert assembly code into machine code. There's generally a pretty direct translation from an assembly instruction to a machine code instruction. When you're writing assembly code, you're pretty much saying exactly what machine code you want. The assembler doesn't try to change things or optimize things like a compiler would. The real hard work of the assembler comes from the labels and memory layout. Technically, it's the linker that does the memory layout stuff, but I'm treating it all as one thing to keep things simple. The assembler needs to take all the chunks of machine code and decide where to put them in memory. Then it can convert all the labels into actual memory addresses. Okay, So the normal flow is you write a sequence of assembly instructions, and you use an assembler to turn it into a sequence of machine code instructions. Super easy. Now, I'm saying turning that sequence of machine code instructions back into assembly instructions is impossible, and it's not. In fact, it's also really easy. You wouldn't get back the labels and stuff, but otherwise easy. If you have a machine code instruction, it's basically nothing to turn it back into an assembly instruction. I mean, if you couldn't do that, then I'd argue a computer wouldn't be able to run machine code programs at all. They're basically the same thing. So what's this video? Was I lying? Is it clickbait? No. When you're trying to disassemble a machine code binary file, you don't have a nice clean sequence of machine code instructions. You get a blob of binary data. And interspersed throughout those instructions, there can be other bits of data used by the program. Things like strings of text, a cute picture, maybe some music. Part of the job of a disassembler, really the most important part, is to figure out how to chop that blob into the right sequence of machine code instructions. Then it's easy peasy to turn it back into assembly. Now, hopefully you're sitting there, staring at your screen, saying, "Jesse, what are you talking about? This is easy. Just go to the start of the program, figure out what the first instruction is, then go to the next instruction, and repeat." I'm hoping you're saying something like that because it would mean I did my job good. It means I can create a curiosity gap, and that helps with video retention. So you're not exactly wrong. I'm assuming it's easy to find the start of the program. Really, a program can start anywhere in its binary, as long as there is a way to jump to that point in the binary and start executing. Something like a separate launcher program or something. Doesn't matter. I'm assuming we're not doing that and we know where the start of the program is. And if you know where to start, you can get the first instruction. There's no question, no guessing, no ambiguity. We know what that first instruction is. Okay, so let's just cut the first instruction out, pretend the second instruction is the first, and by the power of induction, we've got a disassembler. Except, where is the second instruction? If the first instruction was something simple, like a load or an add, or even a static jump, then it's easy. The second instruction is just the next instruction, or wherever the jump said to go. But what if the first instruction is a conditional jump, or a jump to a location given by a register value? Well, that's kind of silly. Why would the first instruction be something like that? It's the first instruction. You can't rely on registers or memory or condition flags having the values you need to execute your program. The first instruction is either going to be a simple one that doesn't jump, or a jump to a specific hard-coded location. Otherwise, the program's just going to do random stuff. That's silly. All right, we know where the second instruction is. And since we know that, we also know exactly what that second instruction is, and how to turn it back into an assembly instruction. Maybe we can use the same argument to say we know where the third instruction is even, and maybe even the fourth, and fifth, and sixth, and seventh, and eighth, and ninth, and 10th, and so on. But eventually, we're going to hit one of those problem instructions that I waved away from the first instruction. A conditional jump or a jump to somewhere given by a register value. Since we're deep into the program now, it's perfectly reasonable that the code relies on those registers and condition flags in memory. They have meaningful data in them. So what do we do now? We don't need to panic just yet. We're not stuck. Since this is the first time we're hitting one of those dynamic jumps, we know exactly what instructions were executed up to this point, so we can easily figure out what the values are that we're using for the jump. So we can just go through those instructions to figure it out, and we're good. So this is where you should be getting nervous. I've led you into one of the classic blunders. I've argued to the point where, eventually, to make progress disassembling, you'll need to know the exact state of the computer at a particular point in the program to figure out where the next instruction to decode is. That's impossible. Let's say you had some program with a bunch of instructions that you've decoded. You eventually reach a conditional jump saying, if the last operation was 0, jump back to some place earlier in the program. Otherwise, go to the next instruction. So the next instruction is either going to be one we've already seen, or it's going to be whatever the next instruction is here. But maybe the program just loops forever and never gets here. Maybe the disassembler doesn't need to disassemble anything from here on, and it's actually done. If a disassembler could perfectly predict whether this conditional jump is taken, or if the program just loops forever and never even reaches the next byte, we wouldn't just have a disassembler. We would have solved the halting problem. And that is provably impossible. Now again, maybe you're thinking, Jesse, you're being silly again. Forget all this halting problem malarkey and just disassemble the next instruction. And okay, fair enough. But if there never was an instruction there, and it's just some data, then by turning it into assembly instructions, you'd be violating my original problem statement by producing output that doesn't match exactly the original simplified assembly code. But hey, maybe I was being too strict. Maybe it's okay if we accidentally turn some data into assembly code. It's not a huge problem, as long as we don't make a mistake and think some binary data is just plain data instead of actually assembly instructions. Let's say we should have at least all the original assembly instructions in their correct places. Now we can just ignore that infinite loop possibility and go on disassembling. Hey, maybe we can just stop worrying entirely and turn all the binary blob into instructions. Except there's another problem. Machine code instructions aren't all the same size. On the Game Boy, for example, a lot are 1 byte long, most are 2 bytes, and a few are 3 bytes. So let's say you have some binary data like this. Is it a jump to address 2336? Or some data followed by a load of the value 23 in hex to the memory location given by register HL? Or some data followed by inc HL? It all depends on where you split the binary data. And you can't have a program that figures that out in all cases without it also being able to solve the halting problem, which again is impossible. I'm glossing over that a bit. You'll have to trust me or convince yourself later. So it's impossible. Did I convince you? Maybe not. If you go back to all the places where I had to stretch a little bit to make my argument, or where the scenario I was creating just seemed unrealistic or silly, those are the holes where pragmatism can slip in. Maybe you can ignore some of the niddly details, like we did with the infinite loop situation, and get something useful anyway. Really, it all depends on the goal. If the goal is to make a perfect disassembler that always produces the right assembly code, then you'll fail. If the goal is to have a useful tool that can help you understand what some machine code does, then you'll probably get a lot closer to success. You just need to find the right corners to cut. Real disassemblers can use a bunch of different strategies to produce useful output. They can use static analysis or abstract interpretation techniques, similar to ones used in compilers and programming tools, to get some estimates of different values at different points in the program. They might use handcrafted heuristics that the developer figured out from looking at a bunch of example programs. Or they could use some AI or machine learning models to help. Will these techniques sometimes fail or make mistakes? Sure. And maybe those failure cases can help people come up with new techniques. So if you ever find yourself working on something that turns out to be impossible, just remember it might be a good idea to ignore that it's impossible and try to do it anyway. You might end up making something useful. Bye.